To introduce Dr. Edward Landing. Ed is a retired paleontologist, the seventh paleontologist of New York State, of the New York State Education Department in all of New York State history. And so he comes to us with a vast degree of knowledge and experiential knowledge about all of human geological history. And so he would like to put a discussion of climate change within that very large context, not the normal Fox News context in discussing climate change. So we are very privileged to have him with his expertise and his knowledge and his depth of thinking about these issues. And please welcome Dr. Edward Landing.
Thank you very much. One small correction, it's actually Ed. But I thank John for the introduction. I thank the audience for showing up. And what I hope to do is give you a talk that has a lot of politics involved in it. And I hope it's a talk that is worth as much as a $225,000 talk given by Hillary Clinton to go in this house. John promises me $225,000. And okay, probably one of the most dangerous things in current culture is modern science, particularly modern natural science. Chemistry, physics, that's fine. You can produce bombs, do whatever. But when it comes to things like evolution or the growth of an understanding of climate science, this is something which is very difficult for the culture to accept. It's difficult for religion to accept. It's difficult for many companies and governments to accept. Modern syntheses of climate change will be denounced as junk science by the right wing, or it will get a both-sided press review, which means that, well, evolution and climate change, there is a continuing controversy when there is none, and we thank New York Times for something like that. Or new syntheses can be quashed, as the North Carolina legislature said that our civil servants will not talk about an acceleration of global sea level rise because it's going to cut down the prices of shoreline property. Now, there are two approaches to reality, and one is the scientific, which is based on observed, repeatedly observable phenomenon, and then you have the deductive approach, which is something in which you put in premises and then you come to conclusions. Now, words have political significance in these discussions. And when it comes to science, we have the word speculation. And speculation really means that you've seen something and you end up thinking, well, is it caused by this or does it lead to that? Hypothesis is you've seen something a number of times, you end up saying, will it always lead to this result, or will it always come from this, these conditions? And finally, we have something called theory, which is diminished in almost every conversation that you hear. And theory is something you have seen this phenomenon time after time. Other people have seen the phenomenon time after time. It leads from the same processes and it goes to the same process. So the fact that the sun rises in the east every day is only a theory. Now, which is the case. And you will have, in the 2008 political Republican debate, the moderator asked all of the candidates whether or not they believed in evolution. And of course, they all went along and said no. Well, both the commentator and the politicians didn't understand that belief is a word that goes along with political activity, or it goes along with faith. And belief is something that you cannot say no to. I believe in a certain type of God. No, you're wrong. Well, that's politically incorrect. You can't say that. But for some reason, you can say that. your theory, as well established as it is wrong, and you're supposed to accept that. Over and over, if you watch CSI, you end up, you hear expressions, our theory of the case is, we've observed something, we've got this evidence, we're going to prosecute in this way. That is really at the level of a hypothesis when it comes to science. But never let the word theory be diminished, because theory is probably the highest basis on which we make conclusions. Next. Now, the most important early proponent of climate change way back in 1837 is a Swiss geologist. He did everything, botany and geology, geography, was Louis Agassiz, who eventually ended up at Harvard, where he started the Harvard Museum, and a strange kind of guy who never accepted evolution and was a raging racist. But the key thing is, he did great glaciology. And he studied these alpine glaciers, these thin valley glaciers, and he studied their sediments and landforms. Next. And what he did was, he noticed, for instance, that living modern glaciers at their base deposit a really unsorted, tumbled sort of sediment that ranges in size from clays to really gigantic boulders. That's a piece of ice that's entrained in there. And this is called till. He also noticed that, hopefully this can be seen, this is the Athabasca Glacier, this is bedrock, and you have scours that have been cut by a moving glacier as it has boulders entrained in the ice and pushed across the bedrock. Next. In living glaciers, I hope these, can you see these slides? Sort of? Okay. In living glaciers, he also noticed such things as this ridge right here is something called an esker. And somewhere right here is an individual standing on this esker. It's built of sediment, but it's built of sediment that was laid down in a melt tunnel underneath the ice. And so they're like elongate hills. And there's also outwash, which is just as the glacier melts, all sorts of sediment laid down in front of a glacier. You've got glacial erratics, which are strange, exotic, sometimes huge stones left behind as glaciers melt. And then we've got a thing called, here's some little French for you, a thing called a roche montagnais, which are really pretty common in parts of New York, for instance. And they consist of bedrock with a steeply dipping up glacier nose and a back that has been quarried out as the ice moved by it. And frequently it is striated. So he noticed these features in the next in the alpine glaciers. And then he went north into the European plain, into Scandinavia, and also into North America. And what he noticed was that generally 40 degrees north latitude, what you ended up seeing was lots of evidence of that unsorted sediment called till. There's a seaside outcrop in Wales. Every size sediment from silt to rocks. He also noted, this is almost recent, striae on Mount Rushmore. Prospect Mountain on Lake George, the very top of it, is covered with glacial striae also. And if you go to Central Park, what you end up seeing is all these glacial features. You've got glacial erratics. Some of these things are really huge in size. You've got roche montagnais. There's a sharp back surface. And these roche montagnais are glacially striated. So there's evidence for an older ice age, it seemed. And this was a big deal at the time because standard science had interpreted these features where glaciers didn't exist as evidence of a flood. So there was a gigantic political and religious reaction against Agassiz at first. He was talking about, oh, that's impossible, continental glaciation, but quite obviously a global flood makes a lot more sense. And he had to fight that for decades. Next. In England, There are outwash deposits, just like in New York. These give gravel pits. Many gravel pits in New York are the result of glacial outwash. And then that neat landform called an esker, laid down as a ridge of sediment in a melting glacier's tunnel. This is one in North Dakota. No glaciers around there, but this thing is running across the landscape for miles. And is further evidence of glaciation in North Dakota. Of what sort? It's not alpine glaciation, it's continental glaciation. Next. So, Agassiz came up with the idea that in general, north of 40 degrees latitude, you had a continental glaciation that, in this case, originates in the Baltic, overwhelms most of Europe. There is an ice cap that develops out of the Alps, the Pyrenees, and the mountains.
Cascade.
Caucasus. Thank you.
Yeah.
Idiot. And the Caucasus Mountains also develop ice. But an important thing that they noticed at this time was that if you look at Britain and the continent, there is no channel. There is no English channel. The reason being that you've piled up all of this water, which ultimately comes from the ocean, evaporated it, laid it down as snow, and created a continental ice sheet. So you had a fall in ocean levels. The fall in ocean levels was 300 feet. Next. This is North America. In the eastern part, Agassiz had also worked here, he was at Harvard. And if you look at North America, the ice sheet comes down to somewhat more than 40 degrees north. But you see Florida is twice its size as sea level fell. And the edge of the continental shelf, shown in blue, is also exposed down to 300 feet in Gulf of Mexico, or in Baja, where the north end of Baja is solid land. Next. Okay, so we've got, this is the modern times. This is about back to 400 million years ago. And we've got this Neogene meaning recent, and you've got Pleistocene meaning almost recent, Ice Age. An Ice Age here. Okay, we've established that. But using similar criteria of landforms and sediment, they've recognized 3 additional ice ages back in geologic time, only since the 1950s. Next. And how's it done? In Siberia, you can find rocks like glacial till, except they're extremely hard, and you know how old they are based on fossils. And that's called a tillite, and this is an ancient glacial deposit. Also in Australia, of course, never any glaciers, but this is in the so-called Permian. Here you've got the bedrock deeply scoured by ice that was carrying boulders. Okay, so we can prove ancient ice ages. Next. And we go back to this. So we've got cold intervals of glaciation, 4 of them. And we've also got what are thought to be hot intervals. And your usual listener to conservative talk radio would end up seeing this temperature curve as so much BS and speculation. It isn't BS and speculation. That curve is really the temperature of the world ocean as determined geochemically. And it's determined over the last 500 million years of cold to warm, and at times far warmer than at present. Next. You could do this sort of analysis right in this very area. This is a quarry north of Tribes Hill. That's 1.5 meters. Collected a lot of these trilobites shown here out of this little quarry. And the trilobites have skeletons composed of calcium carbonate. Calcium carbonate is lime. You can take the lime and you can break it up. You can break the oxygen up into 2 isotopes. I'm not going to be difficult with this. There's oxygen 18, which is heavy. Oxygen 16 is a lighter isotope of oxygen. It is more common. But they figure out what is the ratio of oxygen 18 to 16. If it's cold, for some reason, more oxygen 18 can be put into an animal's skeleton or into lime that is laid down, let's say, on the Florida seafloor. So through time, we can determine temperatures. Next. This is an interval that equals so-called Cretaceous. You just see it as this is the end of the age of dinosaurs. This is about 50 million years. Present day is up this way. And they took two types of very similar organisms, they're called forams. One group, they're single-celled animals. One group lived on the sea floor in the Cretaceous time, and they did the oxygen 18, oxygen 16 ratio. And what they found was that on the sea floor, the temperatures ranged from 80 degrees down to the upper 60s. This is South Florida. In this deep water, what is the present temperature? Deep water. The present temperature is a little bit above zero. In Florida, 70 million years ago. So this was quite a warm time for millions of years. You can also take these single-celled forams that lived high in the water column, and they sampled oxygen 18 and 16 high in the water column, and they show you that high in the water column it was even warmer. And if you compare it to surface water in Florida, which is right here, it was about 9 degrees warmer. So the end of the age of dinosaurs was extremely warm. I'm bringing this stuff up to say that people will always come back and say, well, you've had warm intervals and cold intervals in the past, and it doesn't make any difference. It'll, it's gonna warm up. Or rather, it's going to cool down. There's something wrong with that. That's the purpose of this talk. Next. There are some things that are shared by times of glaciation. It's the configuration of the continents. At present, and 2.5 million years ago, we have a continent south of the Antarctic. It's at the South Pole. It picks up very little heat because the sun just grazes it. Doesn't melt summer snow. In the north, we've got continental glaciation because we've got an isolated Arctic Ocean. It doesn't get a lot of warm water from the Atlantic, and so ice sheets develop there. Let's go back in time next. This is the giant Pangaea paleocontinent. Covers almost all of the world, and part of that continent lies the modern Antarctica, India, and Australian parts are at the South Pole. Again, they're in the proper latitude for continental glaciation to make an ice house. Next. And even further back, 470 million years in the Ordovician, that's the age of the rocks we're sitting on right here. So, Africa is at the South Pole. Lots of evidence of glaciation. Lots of evidence of glaciation in South America. Also, tip of Africa, Saudi Arabia, and the European margin of Gondwana. So the location of continents is important for continental glaciation. Next. What we see that when it comes to glaciers is they wax and wane. You don't build up a glaciation, continental glaciation, and then it just collapses into nothing. It grows. We should be in an interval of 10. We're in an interval of 10,000 years of cooling, but the last 150 years have seen a dramatic warming of 2 degrees. Something is being done, not by natural systems, but apparently by man. Next. And what's being done is, you've heard of the greenhouse effect. There are a number, if they can be read, can those be read down there? You have a number of greenhouse gases that are in the atmosphere, particularly carbon dioxide. Methane is a horrible gas. Water vapor, holds in temperature. HFCs, which are modern refrigerants, also work to, as effect, was not brought up by a bunch of Johnny-come-latelys. It's been worked on for 200 years. About 1820, Joseph Fourier proposed that carbon dioxide is an important greenhouse gas. Svante Arrhenius, late 1800s, also dealt with this. And from the 1980s to 1990s, James Hansen, who was with NOAA, was always being castigated by Congress for talking about global warming and greenhouse gases. Next. Okay, when geologists, John, how much longer do I have?
About 13 minutes.
15?
Yeah.
I will get done quite quickly.
Good.
Geologists talk in terms of a certain cycle that takes place in carbon dioxide. Carbon dioxide is produced and carbon dioxide is buried in some form. What we end up seeing as geologists is that the Earth is broken into a number of major plates, the mid-Atlantic ridges, and there are collision zones. These rifting takes place as a soft area within the Earth called the mantle. This plastic-like rises, and splits the crust, and gives you volcanoes like those in Iceland, which produce a lot of carbon dioxide. And then these cells migrate laterally and push the crust under other bits of crust, and we have huge eruptions like Mount St. Helens. Enormous amount of carbon dioxide is indeed formed at that time. Next. So carbon dioxide will continue to build up unless we sequester it, that is, bury it. And that's happened through geologic time. Sea plants and now land plants build organic structures, and organic structure has carbon in it, has carbon dioxide, and they'll do things like produce leaves and stumps that get buried in the sediments as peat. With greater temperature and pressure, they become harder and harder and more carbon rich, so you get various varieties of coal. Coal is shown in these black seams right here, and coal is basically a land product. You always hear, coal was made from dead dinosaurs. No, it is made from dead land plants. Next.
That is nice.
Oh, yeah. And a similar kind of process, thank you, John, passed out briefly. A similar process takes place in the ocean where indeed you do have photosynthesis, you do have single-celled plants that proliferate. These plants are eaten by zooplankton, little animals, and then by fish. And I hate to use a bad word here, but the zooplankton and fish excrete quite dense, waxy turds. Okay? I hope no one shocked. But these are quite dense and they settle to the seafloor and they do get buried. And with greater burial, this wax heats up and is turned into tar, into the more liquid petroleum, and with even greater heat, as in New York State, much of the petroleum is turned into frackable natural gas. So hydrocarbons, tar, petroleum, natural gas are really products of ancient oceans. Next. That's a second method of burial. And a third method of burial that you may not think of much, if you have uplifted mountain ranges, you have sediment worn off the front. That sediment comes in contact, weathers. It comes into contact with water and carbon dioxide from the atmosphere, and it makes clays and micas, and it makes lime. And that lime with calcium carbonate, that is carbon dioxide, is buried. So it's sequestered. Next, we've changed this whole cyclicity because what we're really doing is we're cutting down an awful lot of forests, burning them, and releasing that saved carbon. We are amazingly successful now in coal mining, which is going under a bit, but also a lot of production of hydrocarbons and natural gas. the carbon that's produced will go into the atmosphere, and we're seeing an increase in amount of carbon dioxide. Some of it will go into the oceans. Carbon dioxide makes carbonic acid, makes it a little bit more acidic, and is working in part to kill corals. We're also killing corals, and this year they say the Great Barrier Reef off Australia is in terrifically bad shape. And finally, the remaining trees do take carbon dioxide out of the atmosphere, but it's a losing equation because we're not sequestering as much as we used to. Next. Now, again, through geologic time, the people who don't like climate change will always say, well, yes, indeed, temperatures have always cooled and warmed, but they'll cool again. It's just a natural process. No, we're not seeing the natural process anymore, because as we come to the recent, what we end up seeing is a cool interval is abruptly changed now into a warming interval of 2 degrees. Continue. And what we end up seeing here are 2 charts. The squiggly lines are temperature back to about 1900. The yellow lines here are carbon dioxide content, which is actually officially measured at the top of Mauna Loa once a year. Older percentages of carbon dioxide in the atmosphere before 1950 are taken from this. This is cut off a bit, but this is an ice core about a foot long. And there are layers in here, dark layers, light layers, equal 1 year. And so you can go in there and you can find little gas-filled bubbles and determine the amount of carbon dioxide. 2-year layers, you can count them back, and you can even find the eruption of Vesuvius. You can find the eruption of Krakatoa. Wonderful preservation of events on Earth. Next. The amount of carbon dioxide that we're producing, this is an old chart, but is increasing dramatically. The coal is indeed falling somewhat, but it has long been, in green, has long been a major carbon dioxide producer, and I had to scratch my head in 2008 when Obama talked about clean coal. There is nothing clean about coal, from the carbon dioxide to the sulfur. Obama talks about clean natural gas. Well, but the amount of carbon dioxide produced by natural gas at present equals the amount of carbon dioxide produced by coal in 1950. So these are, fossil fuels are real losers when it comes to planet change. Next. And this planet change, of course, is seen by the melting of valley glaciers, which is very dramatic. It amounts to gigatons of water that are melted on the west side of Antarctica by warmer currents. This is the depth of water at high tide at the Battery, which is the harbor at the very end of New York City. And there has been a 10-inch increase in the height of high tides in the past century. So things are happening very quickly because the water's coming out of here, the water's coming out of there. And indeed, when it comes to most continents, you end up seeing that most major cities are recording increased heights of sea level. So that's called eustatic rise. Next. Now, you also hear some things like about melting permafrost, or what's getting so bad, whatever. Well, actually, this is a serious thing. Permafrost in Canada, Siberia, is melting so fast that you can actually cook on it. Yeah. It is coming out so fast in some places that you have fountains of methane. And methane is an incredible greenhouse gas. And what I find most intriguing, I don't have a scientific name for them, but there are huge craters in Siberia and Canada where methane has just blown out to the surface to become part of the atmosphere. Next. Now, if we melt, the usual estimate is melt Greenland plus Antarctica, get 300 feet of sea level rise, perhaps by 2200. What this does is it floods this blue area of the maps and basically wipes out a number of, in this case, European countries, pretty much all the major cities, also in North America. And that's one effect, the wiping out of cities and the movement of people. But I think there's an even more important effect, which is global hyperwarming, that I'll get to at the end of the talk. Next. If we look at the edge of a continent, you always have shallow sea, and then you have a continental slope that drops off quickly, and then it gets relatively shallow. Now, the shallow sea is something that a lot of light gets through it, there's a lot of photosynthesis, a lot of oxygen. But once you get below and it starts to get dark, you lose oxygen. And with animals still living there, and with dying things sinking, you have an interval from 900 to 2,000 feet where there's almost no oxygen. And then, oddly, the very deep sea floor is oxygenated. You would think that it would be anoxic all the way down. How is this possible? It's possible next only because of a thermohaline circuit that takes place in the ocean and is caused by the fact that you have cold poles with extremely high winds. The extremely high winds will take the warm water of the Gulf Stream and cause a lot of evaporation. So what you have is very dense seawater with a lot of salt. In addition, these winds up here and here are extremely cold, and cold water is dense. So if you have continental glaciation, then you will have deep water circulation. But if you don't have those, then you will completely change the nature of the oceans. Next. I've done 5 slides left, I think. I've done a lot of work in shallow water rocks in eastern North America and elsewhere, and also in what includes the tectonic slate belt of New York and Quebec and Newfoundland. Next. And I can add something to this idea that the melting of glaciers raises sea level. There's another effect that takes place, and effect 2. Next. What happens if the edge of a continent is inundated by water? This map here shows how much light and heat is radiated from sand, from deserts, from crop areas, and you get a pretty reasonable amount of reflectance from the land surface, reflectance of heat to space. But if you cover lands with shallow seas, those shallow seas pick up an awful lot of heat and will heat the world ocean. Right off, you're going to have a problem there. Hot water doesn't have a lot of oxygen. There won't be a lot of things that will want to live there. But this will be an effect as Greenland and Antarctica melt and we have sea level rise. Next. This is one of these incomprehensible charts that geologists put together, but if you really do close work in the tectonics, you can divide the rocks into black intervals versus green. There's about 5 black intervals up here, a long one here, another one here. But what I always see is that these black intervals, black organic rich shales, always equals times of high sea levels. Always. Green shales, red shales equal times of very low sea levels and oxygenation of the seafloor. Next. So basically this is what happens at a time that I call global hyperwarming. This is beyond the greenhouse effect, in which temperatures are controlled by carbon dioxide. This is a phenomenon where temperatures are increasingly controlled by the presence of expanding seas that get extremely hot on continents. The low oxygen zone, the dead zone that always exists off of continents, does two things. It gets more stronger, it thickens, it gets into shallow water. It thickens and it goes down the slope. So we have huge amounts of dark sediment that are produced. We will have shallow seas that don't have much in the way of fish and everything to eat because there's no oxygen. So next, this is what America will look like with the final melting of all the Antarctic Greenland ice, as well as the thermal expansion of seawater by increased heat. I predict a 600-foot increase, 300 feet more than simply melting the ice. You'll have hot water that itself expands, and North America would look something like this. The Appalachians above water, central U.S., the Rust Belt, well, that's the Rust Belt, pretty much gone, and the Canadian Arctic would be underwater and finished. Next.
That's 600 from today's level?
Pardon?
That's 600 feet from today's level?
600 meters.
Meter.
Yeah.
From today's level?
From today's level.
Over what period of time?
And that, in that case, we are probably, I should have said that, we are probably talking on the order of 4 to 12 million years. An awfully long period of time based on what I've seen in the real geologic past in eastern North America. Okay? Now, if we've got this time of glacial hyperwarming and an awful lot of dead ocean into shallow water and into the deeper water, anything that dies will sink to the bottom and get preserved. And so you'll have an awful lot of organic-rich sediment. And that organic-rich sediment will be the source of future petroleum. So if any intelligent life lives or comes here after 4 to 12 million years, they can really start the cycle over again with us. Thanks for your patience.
Thank you.
Yeah.
This summer was unbearably hot. Do you foresee future summers this bad?
Well, I mean, the thing is that when you're getting down to this, then you get into the proposals that there will be climate irregularity. And there could indeed be, truly a number of horrendous summers, followed by some cold summers. I can't quite, answer that. It's just this through June. This was the hottest year on record,
July also
Through
now.
July.
and July also probably.
Yeah. So I'm sorry.
Go ahead.
There's no possibility that within our lifetimes we will not have an Earth.
That we will then.
Not have an Earth.
Oh no, there will simply be an Earth. I mean, you've got an 800-degree Venus. It's hot as anything. And one thing always to keep in mind is that we talk about these things as greenhouse gases, but carbon dioxide is important. They calculate the Earth's temperature would be almost like Mars, 55 degrees below zero, without carbon dioxide. But we've got enough of it to make it habitable. But you get too much of anything that's natural, and that's a pollutant. And so now we've entered a world where carbon dioxide, is a pollutant. Yep.
I'm not sure that saying I enjoy your talk is the best but actually I do. And I love the term living glaciers.
Yeah.
I love that term.
Yeah.
And I noticed that in your talk, the only thing that I remember hearing as a way to take carbon out of the atmosphere is something you call carbon sequestration.
Yeah,
And my understanding, I've heard it said that organic agriculture is probably one of the best ways to sequester carbon.
yeah.
Can you speak to that?
Well, there are so many different ways. A guy once said to me that probably the best way to sequester carbon is to not recycle.
Explain.
In that what you would do is you simply bury all the carbon, food and all the carbon, the wood, utterly bury everything. And that would be a way to keep, carbon, from recycling. But there are, indeed so many different ways to do carbon sequestration. One was that the coal companies were talking about, they would be basically mixing it with gypsum and then burying the gypsum. But the amount of energy that seems to be required for that is just a bit too great. Yeah, many ways for sequestration. One thing can you improve things? Yeah, I think you can improve things. One thing Australia has to do is to stop all the orange groves and stuff that they have that is flushing all this sediment into the Great Barrier Reef and is killing large parts of it. And it's really an international problem.
Well, I have two quick questions. First quick question is the 600-meter sea level rise.
Yeah.
When will that happen? What year will that happen? And my second question, like 2100, 2200. And my second question is, what are the odds of like a runaway greenhouse effect, like on Venus, happening here?
Okay, well, as sea level is increasing now, even with that 10-inch increase at the Battery at the end of New York City, the sea is coming in a little bit more, so that effect of the hyperwarming it's really just starting. Yeah, to melt all of this ice, they're talking about 2200. That's their estimate. Yeah.
And then the runaway greenhouse effect?
And what?
The runaway greenhouse effect?
And that then would indeed be following, and I'd be a fool to speculate too much on that, but it's certainly well beyond our lifetimes. But as that sea gets beyond, as that 300-foot sea level rise increases, we're going to be wondering about, boy, it's getting hotter than it ever was. Yeah.
Jill Stein made a reference
Yeah.
to Margaret Davidson, and in a way, talking to some insurance meeting on the West Coast thing that by 2050 or 2060, sea levels could rise as much as 9 feet. Any comments? Have you heard of this?
Yeah, I indeed have heard of that, yeah. That within a century,
No, that's talking about 2050.
Yeah. And I've heard of that, and I've also heard it being put off by a century.
Oh, okay.
So, yeah.
I like the sentence.
Anybody else? Yep.
Yeah, so do you foresee humanity being able to survive on this planet for 7 generations? That's what we're supposed to consider 7 generations.
Well,
2 generations.
Yeah.
2 generations.
I'm sorry, did anybody see a green spiral notebook? I haven't seen it. I'd like to get it back.